So the last section I want to cover for this week is levers, and levers are pretty straightforward as well, but it's going to make us talk about torque for just a couple of minutes. So we're going to look at that for a second. So what's the purpose of a lever? So a lever changes the amount and or the direction of force. So it could do both, but it's going to do at least one. You'll see here, this lever changes the direction of force. You have force down, and I move it by pulling up. Here, both forces are in the same direction, so it just must change the amount of force. And then in this particular example, we have my force upward and an effort force down. So these are the three types of levers we could have. So a lever is just a rigid bar. We don't want it to have any flex in it. If it has flex in it, that's going to change our force numbers. So we're going to think of it as a rigid bar placed over a pivot point, and this is our pivot point, and we call that the fulcrum. And we're going to find there's three classes of levers, and we'll look at those separately. First of all, let's think about the law of simple machines. The law of simple machines, going back to our very first video, says that input work equals output work, or effort force times effort distance equals load force times load distance. Now, sometimes it's not easy to find the effort force or to find the effort distance. Likewise, it's not always easy to find the load distance and the load force. So for some simple machines, we use torque. Now, I'm going to quickly talk about torque, but I know you've talked about torque with Jeff. So torque is just a twisting force, okay? It has the same formula as work, so force times distance, but it's not the same because this distance is not in the same direction as force. In fact, you'll see the distance is here, but the force, instead of being parallel, the force is perpendicular. So they make a T shape with each other. So this is the force that I'm applying at the end here. So this is my force times the distance from the pivot point. So on the nut, you would have, here's your pivot point, and a wrench is going to place a force on the outside edge of that nut. If we know how big it is, we can figure out how much force it is. Okay, so it's not equal to work, but it's directly proportional to work, meaning the torque in on a simple machine will always equal the torque out on a simple machine. So just like work, torque in equals torque out. Okay, so they're kind of related. You can think of them as being similar. It'll help you out. But one's the twisting force and the other one is actually the amount of work that you do. So for some simple machines, like I've said, input torque equals output torque, and torque can be easier to measure when we're talking about levers, wheels, and gears. Okay, or levers, wheels. I think I actually spelled lever wrong. So levers, wheels, and gears. Okay, so you'll see if you think of the formula, you can think of it as the exact same way. So why are they related? I'll show you why they're related, and then we'll look at how you just use the torque one. So why are they related? Well, see this diagram. This is a lever. This is my pivot. Okay. If I am using the torque formula, I would do the force that I'm pushing at the end. So I would use this force times my pivot distance. Over here, I would use this pivot distance times whatever this force is. Okay, you'll see now the arrow is shorter, is showing how far I'm moving the force, but because it's thicker, it's a bigger force. So on this end, if you think about the distance, the further from the fulcrum, the longer the distance I have to push. That's like work. Work would be the force times the distance straight down, but that distance is often difficult to measure, but I can measure the distance from the turning point quite easy. Here, we have a large force that we're moving, but you'll see it's only going a small distance. And that small distance is also a small distance from the pivot point. So they're really closely related, okay? So the ratio, the change, I don't know how to best describe it. The change in height here is directly proportional to the distance from the pivot point, which is why we can use torque instead of the work formula. Hopefully that makes sense. But anything that's turning or rotates, like a lever, gears turn, we're going to think of it using torque. So instead of the distance that the force moves, I'm going to think distance from where it turns. So first of all, let's talk about 3 classes of levers, and then we'll do a couple math questions. So a first class lever, the fulcrum, that's the pivot, is between the effort force and the resistance or the load. Okay, so it's in between. The effort pushes down and the load pushes down, but when I push down with my effort, output is up. Output is always equal and opposite to the resistance force. Examples, scissors, they're a great example, and pliers. Anything like that that you squeeze, typically they're going to be an example of a lever, and it's a first class lever because you have load on one side, fulcrum on the other, and force on the other. Okay, so that's an example of our first class lever. Oops, I guess I didn't need to write that in. I had it on, I'm not used to using animation. So the output force created by the effort is always in the opposite direction of the resistance, but it's equal to it. Now there's 3 mechanical advantages that we can have with a first class lever. If the fulcrum is perfectly in the middle, you have a balanced lever, which means it's a mechanical advantage of 1. Might change, it changes the direction of my effort. It lets me push down to lift something up, but it doesn't multiply my force. If the fulcrum is in the middle position or is closer to the effort, so here, it's closer to the effort force. In this case, my mechanical advantage is less than 1, so my force is not multiplied. In fact, I have to put more force in to get work out. Scissors are like that, but why? Well, there's an advantage to it. I might have to put more force in, but I can apply it over a longer distance. Imagine if you had maybe not used, now there are some scissors that are different than this, tin snips. If you look at tin snips, the handles are long. I'm going to pause this. I'm going to go get mine and I'm going to show you. Okay, so I'm back. So scissors, this is an example of what I've given you. These are scissors that I usually use for sewing. So they're cutting fabric, paper, that kind of thing. I shouldn't say I cut paper with my sewing scissors. These are a retired pair. If you cut paper with my sewing scissors, you are liable to lose your head. But you'll notice the pivot point here, it's actually relatively close to the middle of this blade, but it's a little bit closer to where I put my effort. The blades are nice and long. These have a mechanical advantage less than 1, but what's the advantage? Well, it allows me to cut a long distance because what I'm cutting doesn't have a lot of resistance. Fabric, paper, it doesn't take a lot to cut it. So in this case, it makes sense to have scissors that don't multiply my force. Instead, they just spread my force out over a longer distance. Now, in the second example down here, the pliers are a really good example of this. The pivot point, this turning point, is further away from where I put my force. And when that's the case, it multiplies my force. So I went and grabbed another pair of scissors. We were cutting aluminum for some fascia and bought these things. In this case, you'll notice I apply my force way far away from the pivot point, but my blades are very short. Why? Well, these are meant for cutting metal. Metal has a lot of resistance. This decreases my force. It's no good for cutting metal. It's only good for cutting light things. These scissors, because the fulcrum is closer to the tip of the blade, closer to what I'm cutting, it multiplies my force, making it easier for me to cut it. Believe me, there's still a chore to work with because there's a lot of friction in these. Maybe they need a little lubrication to work better. Pliers, why would pliers often have this shape? Well, usually when you're using pliers, you want to apply a lot more force, or you need to increase your force. So with pliers, You'll put your force, it's not just to have enough room for your hand, that's part of it, but you'll apply your force far away from the pivot point so it multiplies your force out and makes it easier for you to work. Now, if you have long nose needle nose pliers, you're going to be able to apply less force with those than you will with short nose ones. One of those just kind of random things. Okay, so that tells you a little bit about how your mechanical advantage will work. First class levers are the only ones that can decrease our mechanical advantage as well as increase it. All right, there's another type of lever. It's a second class lever. If you've used a wheelbarrow, you've used this one. For this case, we put the fulcrum at one end. So it's like the wheel of a wheelbarrow. The load or the resistance goes in the middle. So that makes sense for a wheelbarrow. And then we lift on the other end. It always changes the direction of my forces. So I lift up to lift upwards on a load that's pushing down. So you'll see that the resistance or the load will always push in the opposite direction of my effort force. And it always has a mechanical advantage more than one. It can never have a mechanical advantage less than one. It'll always have a mechanical advantage more than one because the distance of the effort will always be longer than the distance to the resistance. Now, if you come to applying it to cars, I always try to find an application to connect it to vehicles, because otherwise, why would they say I have to teach you this section? It must connect somehow. Brake pedals could be first or second class levers. You might not have thought about that. So we have a pivot point. So here's our pivot point. On this one, here's a pivot point on the other one. So in this case, if the pivot is at the end, and it's applying force on the master cylinder, that's our load, and my effort goes on the pedal, what type of lever is this one? The load is in the middle, the pivot's on the end, and my effort is at the very end of it. This is like the wheelbarrow. There's my wheel, there's my load, here's my handles. This is a second class lever. So it takes the force that I put on the pedal and it's going to multiply it to the master cylinder. So I only have to apply a very small amount of effort in order to apply a larger force on the master cylinder, which will then respond to my brakes. Well, what about this scenario? So here's my pivot. Here's my master cylinder, and there's my pedal. So this is my effort. The pivot somewhere's in the middle and the master cylinder is on the end. This is my load. If the pivot's in the middle between the two, or the fulcrum's in the middle, this is a first class lever. Now you'll see my effort is a long way from the pivot, which means it takes my force and it multiplies it to the master cylinder. So a couple examples of, do we use levers in vehicles? 100%. And it's more than in just using wrenches. That's the whole principle behind how brake pedals work, gas pedals, all of that kind of stuff. All right. Okay. The last type of lever I want to talk about is a third class lever. A third class lever has the fulcrum. It's on one end, so it looks like a second class, but you'll notice my effort goes in the middle and the load is on the end. So a shovel. It's a really good example. I hold the end of the shovel. That's where I tip from. My hand is in the middle and the snow or gravel or whatever is on the other end. So that's our third class lever. It always has a mechanical advantage less than one, unfortunately. But it does make it easier to lift just based on where we can lift from. But it never multiplies our force. It always decreases our force. So a couple of lever math questions, and most of our lever math questions, we'll do a first class lever and a second class lever for a lever math. We won't deal with a third class lever. These ones are just good ones for kind of applying to us. So the first thing I want to think about, we said torque is related to, make sure I find my right question, my right pages here. Torque is related to work. So I want to know what's the torque on the effort side in foot-pounds. Now, you know that you measure torque in foot-pounds. Sometimes it's Newton meters, But we can measure torque in foot-pounds. We can use pounds as the force, and then foot is the distance that it's applied from the set turning point. So on the effort side, we have 16 pounds of force. So torque is equal to force times distance. So I have 16 pounds turning this lever. It's a seesaw. It's turning it. Can't turn it all the way, but it's turning it part of the way. Times the distance. 5.5 inches is how many feet? Well, we're going to divide it by 12, and you will find that that's 0.458 feet. So you do pounds times feet to get foot-pounds. And that happens to leave us with 7.3 foot-pounds of torque. So pretty easy. If this machine was 100% efficient, what distance would we have to have over here? Well, we know the torque in has to equal the torque out. We already know what the torque in is. The torque on my effort side is 7.3 foot-pounds. That has to be equal to force times distance on the other side. We know how many pounds of force we have on the other side. So 7.3 foot-pound is equal to 32 times whatever distance from the middle we are. We don't know where it is. We just rearrange. We divide by 32. And the distance is equal to 0.23. What units are on that distance? Foot-pounds divided by pounds leaves me with feet. Or foot. Feet or foot. I don't think you could say foots. So 0.23 feet, which if we multiply by 12, that would give us 2.75 inches. Okay, so pretty easy to calculate, not too complicated. All of the math is that easy. You just kind of think about how it's connected. Whatever it is on one side, it's equal to on the other. And like I said, if you forget about torque, if you think about it like the work formulas that we have done, they're similar. Okay, example 2. You'll notice it's the same picture, but we're just asking some other things. This time I want you to think about mechanical advantage. It's the same formulas that we had in the last 2 sets of slides. If you don't remember the formulas, you can look them up. I'll just make a note of them here. Actual mechanical advantage uses distance because it's not affected. Actual mechanical advantage uses force because it can be affected by the force of friction. So it's going to be the force of the effort. I wrote that backwards. It's going to be force on my load divided by force of effort. Ideal mechanical advantage uses distance. And it's going to be the distance of effort divided by the distance of the load. Okay. So those are 2 formulas. So we want to use force to determine the mechanical advantage. So how do I do that? Well, I get 32 pounds of force out. I put 16 pounds in. How much was my force multiplied? 32 divided by 16 is 2. My force has doubled. Using distance to find mechanical advantage, I think about the effort distance divided by the load distance. So 5.5 divided by 2.25. You'll notice it's different than what we calculated before. That means we're probably not efficient. 5.5 divided by 2.5 leaves me with 2.4. My force should have been multiplied 2.4 times, but it was only doubled. Is it efficient? Nope. We can prove it. 2 divided by 2.4 leaves me with 83% efficient. So there must have been some friction in there somewhere because the ideal mechanical advantage was less. So again, you're using the same formulas over and over and over and over. Last one. Lug nuts usually need 110 Newton meters of torque. The nut is 21 millimeters in diameter and the wrench is 30 centimeters long. How much force do you need to apply to loosen the nut? This is one of those questions that you look at and you go, seriously, what are they asking? It's an easier question than you think. First of all, it tells you how much torque you have. What do you know about torque? Torque equals force times distance. So I can use torque to find out how much force I put on the wrench. So it'll be force here. This is how much force I need to loosen it times distance. So I use 110 Newton meters equals force. If I have Newton meters out, should I put centimeters or meters in? I'm going to have to put in meters, 0.3 meters. So times 0.3. 30 centimeters is 0.3 meters. Divide both sides by 0.3. How much force do you have to put in to get 110 Newton meters of force, of torque? Well, the force is going to be equal to 333 newtons. Make sure that number actually works out right. 110 divided by 0.3. Yeah. Oops, 366. I have scribbled notes because I didn't print this question off. Let's just change that number. 366 newtons. And somebody, hopefully somebody will say, oh, wait a second, you didn't round that very well. And we'll put 367 newtons. Okay. How much force is on the outside edges of the nut? Well, this is really like having a lever. There's my pivot, and the resistance is the outside edge of the nut. Now, let's draw it. There's my pivot. All the way across, this distance is equal to 21 millimeters. Okay? So what is the distance from the middle to the edge? That would be like our radius. So the radius is equal to 21 divided by 2, which would leave us with 10.5 millimeters. Oh, but we've done everything in meters. How do we change that? Well, we move our decimal 3 places. 0.0105. Throw a conversion chart in if you need to. Okay, that's how many meters. So if we want to know how much force is on the outside, we know the torque from my force at the end of the wrench has to match the torque on the bolt. They have to be equal to each other. Torque in equals torque out, just like work in equals work out. So torque equals force times distance. So, oops. So if we have 110 Newton meters, that is equal to the force on the nut times the distance from the pivot. And the distance from the pivot is 0.0105. It's a very small distance. What's going to happen to that force? You should see the force increase. The force is equal to 110 divided by 0.0105 leaves me with 10,476 newtons. Our force has been massively multiplied. If I want to know what the ideal mechanical advantage is, we're just going to compare the two distances from the pivot point. My effort was put 0.3 meters from the pivot. The load was where the edge of the nut is. It was 0.0105 meters from the pivot point. It was really close to the pivot. The mechanical advantage happens to be equal to 29. So using a wrench that's 30 centimeters long, 30 centimeters, if you need a reference point, I lost my ruler somewhere. So I had a standard length ruler here. Not sure where I set it down. So would be about like so. So that might be a little longer than your normal wrench. I know a torque wrench is typically longer than 30 centimeters, but you're getting your force multiplied by 29 times. That's absolutely insane. Now, if you have flex in the wrench, they're made out of rigid materials for a reason, because if there was flex in it, you would get less mechanical advantage. But using a wrench, your force is multiplied like a crazy, crazy, crazy amount. Hopefully those questions kind of make sense to you. There's just a couple of questions on them on SAM. Your test for this section will be a lot of kind of described questions, kind of like that video question that you had for your physics section. So it's going to be not quite as mathy. You'll have a little bit of math. So if you get a little bogged down in that, hopefully the rest of it will balance and okay for you. And that finishes off this section. The next one up is going to be gears. And then we'll look at pulleys. So 2 more lessons, and then you're finished with forces. So finished with forces and finished with math. That'll be a good feeling.